Hello, welcome to the Learn English Lab. Today's podcast, English Listening Practice podcast topic name is 30 plus C1 level vocabulary on astronomy. Welcome to the deep dive. Today we are launching kind of a special mission. It's designed specifically for you, yes, you the listener, aiming for that C1 level in English proficiency. Our goal, well, it's to climb from everyday conversational English up to, real sophistication by mastering the language of the cosmos itself.
That's exactly it. We're not just listing words here. This is about deep contextual learning. We're taking this pretty hefty list, over 30 astronomy terms, and really transforming them. They won't just be dictionary entries anymore. The idea is to make them useful tools for, nuanced, really knowledgeable conversation. It's less about just reciting definitions, much more about mastering what we call precise articulation. And that really is a hallmark of advanced language skill, C1 level. I think that phrase, precise articulation, that's absolutely key, isn't it? And the scope of this deep dive, it feels suitably vast, almost mirroring the universe we're talking about. We'll kick off with the really big picture, ideas, origins, the scale of everything. Then we'll zoom in a bit, look at specific things floating out there, celestial objects. And finally, we'll dig into the human side, the science, the engineering, the organizations that actually let us explore this incredible domain.
Yeah, it's going to be quite a journey. So let's start this deep dive right where science thinks the universe itself began.
Okay, let's dive in. The biggest idea for how everything started, the Big Bang. It's pretty much the foundational concept in cosmology, right? The theoretical beginning. Some call it the primordial explosion, the event that basically kicked off the entire universe into existence.
Exactly. When we talk about the Big Bang, we're discussing the cosmic origin of everything, space, time, matter, all of it, as we currently understand them. But, what makes it the leading theory? It's not just a neat idea, it's the data, the evidence. And the most definitive piece of evidence that scientists point to, that's the cosmic microwave background radiation, or CMB.
Okay, explain that for us. What exactly is the CMB and why is it such a big deal?
Right. So the CMB is essentially this faint, incredibly uniform glow that fills the entire universe. Okay. Think of it like the leftover heat or light from that incredibly hot, incredibly dense state right after the Big Bang. It's been traveling across space for billions of years, stretched out and cooled down by the expansion of the universe. Its temperature is almost perfectly uniform, whichever direction you look, and that uniformity, it's like a fingerprint. Powerful evidence that the universe did start from a single, incredibly hot, dense point.
Wow.
Without the CMB, honestly, the Big Bang would still be, maybe a strong hypothesis, but more speculative. With it, it becomes the absolute backbone of modern cosmology.
That evidence really does sound compelling, but I also find the philosophical side of it just as interesting, the questions it raises. The debates often seem to circle around time itself, like what happened before the Big Bang? Does that question even make sense if time and space began then?
It really pushes the boundaries, doesn't it? It forces us to think about causality, about existence itself, maybe outside the frameworks our current physics can even describe.
Yeah.
And when we try to conceptualize all of this immense reality, not just the physics, but the whole structured nature of it, we often reach for the word cosmos. It means more than just universe or space. The cosmos implies the universe seen specifically as a systematic whole, as having a kind of cosmic order.
Systematic whole. It sounds like a word with a bit more weight to it, implying structure maybe. Where does that come from?
It's an ancient idea, actually. It comes straight from Greek. Cosmos, it meant order, good order, even adornment. It was seen as the direct opposite of chaos. So philosophers, theologians, thinkers throughout history, they've used cosmos precisely because it suggests this inherent structure, a harmony, an interconnected system. It makes it distinct from just thinking of space as a random jumble of galaxies. Using cosmos elevates the discussion, suggesting deep connections between everything.
Right, I see. And building on that structure, we get the adjective form cosmic, which describes anything related to the universe, universal, maybe extraterrestrial. But you mentioned its specific usage. It relates to observation, but also, kind of surprisingly, to human safety.
Yes, that's a fascinating contrast, isn't it? How something so cosmic, so vast in scale, translates down to very real, localized risks. Take cosmic rays. These aren't like light rays, they're actual particles, often atomic nuclei stripped bare, flying through space at incredible speeds near the speed of light. They originate from really violent, distant events. Things like exploding stars, supernovas, maybe active galactic nuclei.
And they pose a risk to astronauts.
A significant one, yes. Because they're so energetic, they can penetrate typical spacecraft shielding. For astronauts on long missions, especially outside Earth's protective magnetic field like a trip to Mars, The cumulative radiation dose from cosmic rays is a major health concern. It's a huge challenge for aerospace engineering to figure out better shielding without adding impossible weight.
So understanding the cosmic scale, these rays, is directly tied to practical engineering for space travel. That's interesting.
Absolutely. And on the flip side, observational astronomy is all about capturing cosmic events, seeing those distant supernovas, galaxy collisions, nebula formations. That's how we piece together the history and the evolution of the cosmos itself. We're observing these cosmic phenomena to build our understanding. #TAG our place in the galaxy.
Okay, let's zoom in a bit from the whole universe, right down to our own cosmic neighborhood. We live inside the Milky Way. That's our home galaxy. That familiar, beautiful, sprawling galactic band you can see arching across a really dark night sky. It holds our solar system, plus billions and billions of other stars.
That's right. The Milky Way is what we call a barred spiral galaxy. Think of a giant pinwheel, maybe 100,000 light years across. It's enormous. And the reason we see it as that faint, hazy band is because we're inside it. We're looking edge on through the flat disk part of the galaxy where most of the stars, gas, and dust are concentrated.
Ah, okay. That makes sense. You need special conditions to see it well, though.
You really do.
Yeah.
You need to get far away from city lights. Finding proper dark sky locations is crucial. Light pollution is a massive problem for astronomers, both amateur and professional. It just washes out the faint light from space.
It's amazing how much that visible band, the Milky Way, has influenced human culture over millennia.
Oh, profoundly. Just the sight of it. This star river, as some cultures called it, it's so fundamental. You find myths and legends trying to explain it all over the world. Spilled milk from a goddess, a path for souls to the afterlife, a celestial serpent. These stories show humanity trying to weave meaning and structure into this vast, luminous thing hanging above us. It really highlights the deep connection between astronomy and, well, human civilization.
And when we talk about the space between the stars, within our galaxy or even beyond, we use the term interstellar. So occurring or situated between the stars, spanning that immense, incredibly cold, mostly empty cosmic void.
Interstellar, yes, it's a great C1 word because it signals a specific scale. We use it when we're talking about things happening between star systems. For example, interstellar missions. That term refers specifically to spacecraft like Voyager 1 and 2 or the Pioneer probes. They've actually left the sun's direct influence, the heliosphere, and are now physically traveling through the space between our star system and the next.
That journey must be incredibly long and face challenges we can barely imagine.
The distances are staggering, certainly, but it's not just distance. While interstellar space is mostly vacuum, it's not perfectly empty. One big challenge for astronomers trying to see across the galaxy is interstellar dust clouds. These aren't just little puffs. They can be vast, dense regions of gas and tiny solid particles. This dust absorbs and scatters starlight, especially visible light. We call it extinction. It effectively dims or completely hides objects behind it.
So you need other ways to see through it.
Exactly. That's why infrared and radio astronomy are so important. Those longer wavelengths can penetrate the dust much better, allowing us to peer into obscured regions, like the galactic center or star-forming areas. So interstellar captures both the scale of the journey and the nature of the obstacles.
Okay, now let's shift focus. We've looked at the big picture, the galaxy. Now let's talk about the specific things in space, starting with the most general term, celestial body. This basically means any natural object out there, right? Planets, stars, moons, asteroids, comets, anything naturally occurring outside Earth's atmosphere.
Precisely. It's a fundamental umbrella term. And I quite like its sort of formal dignity, celestial body. That sounds significant. And as you touched on earlier, well, scientifically, it's just descriptive, culturally.
Yeah.
Wow. The personification of celestial bodies is just constant throughout history. Greek gods, Roman gods, Egyptian deities, Mayan cosmology, cultures everywhere saw these points of light, these heavenly objects, not just as things, but powerful beings, gods influencing everything from harvest to fate.
Fascinating. Let's narrow it down to stars, but maybe the smaller ones. The term dwarf star, what does that describe?
A dwarf star is, relatively speaking, small in size, low in mass, and dimmer than stars like our sun. But small here is relative to other stars. They're still enormous. And interestingly, these small stars are actually the most common type in the universe, specifically red dwarfs. These are the coolest, dimmest stars on what we call the main sequence. They vastly outnumber stars like our sun in the Milky Way.
And they burn their fuel differently.
Very differently and much more efficiently. They fuse hydrogen into helium much, much more slowly than larger stars. A key process is convection. The star's internal churning constantly mixes the hydrogen fuel, allowing them to use a much larger fraction of it over their lifetime, compared to a star like the Sun.
And that slow burning means they live for a very, very long time.
An incredibly long time. We're talking potentially trillions of years for some red dwarfs. That's far, far longer than the current age of the universe, which is about 13.8 billion years. Their long lifespans are just staggering.
Trillions of years. Wow. And that longevity, that connects to astrobiology, the search for life.
It's a crucial link, yes. Astrobiology is the field studying the origin, evolution, distribution, and future of life in the universe. And red dwarfs are prime targets. Why? Because of that stability and longevity. If a planet orbits a red dwarf within its habitable zone, the region where liquid water could exist on the surface, it has an enormous amount of time. Billions, even trillions of years for life to potentially arise, evolve, and maybe even become complex.
So more time means more chance.
That's the thinking. But there's a catch. Always a catch in space. Because red dwarfs are cool, their habitable zone is very close to the star. Planets orbiting that close are likely to become tidally locked, meaning one side always faces the star, leading to extreme temperature differences, one side scorching hot, the other freezing cold. That presents a whole different set of challenges for potential life.
Right. Constant daylight on one side, eternal night on the other. Okay, that detail really shows the complexity, and that leads us perfectly to planets outside our solar system, the exoplanet. So, any planet orbiting a star other than our sun, an extrasolar planet.
Yes, exoplanets.
Yeah.
The study of these has just exploded in the last couple of decades. It's been a genuine revolution in astronomy. Before the 1990s, we assumed they existed, but we hadn't definitively found any. Now, we know of thousands of confirmed alien worlds orbiting distant stars.
How did we find so many?
Several methods, but a key one was space telescopes, like NASA's Kepler. Kepler stared intensely at one patch of sky for years using the transit method. It looked for tiny periodic dips in a star's brightness. That dip often means a planet is passing in front of the star from our point of view, blocking a little bit of its light.
Very clever. And what's the ultimate aim now that we know they're so common?
Well, the grand goal, the dream, is finding signs of life. Now that we know exoplanets are everywhere, the focus is shifting towards characterizing them. We want to analyze their atmospheres. Future telescopes, like the James Webb Space Telescope, are designed to do just that. We're looking for biomarkers.
Biomarkers? Like what?
Gases in a planet's atmosphere that might indicate biological processes.
Yeah.
Things like oxygen, methane, ozone, water vapor, especially if found together in certain combinations that are hard to explain just through geology. Finding those would be, well, monumental. We're not just planet hunting anymore. We're searching for genuinely habitable worlds.
Okay, we've covered stars and planets. What about those visitors that sometimes swing through the inner solar system? Comets, described as icy wanderers.
It's a good description. A comet is essentially a leftover chunk from the formation of the solar system, usually composed of ice, frozen water, methane, ammonia, carbon dioxide mixed with dust and rock particles. Like a dirty snowball, really. Most of them live way out in the cold, dark regions, like the Oort cloud or the Kuiper belt, far beyond the planets.
But they become spectacular when they come near the sun.
Exactly. As a comet approaches the sun, the solar radiation and solar winds start to heat it up and vaporize the ices. This releases gas and dust, creating a glowing atmosphere around the nucleus called the coma. And then the pressure from sunlight and the solar wind pushes this material away, forming the characteristic tails, usually two tails, actually.
Tails.
Yeah, often a bluish gas tail made of ionized gas, which points directly away from the sun, pushed by the solar wind, and then a broader, often curved, whitish dust tail, composed of tiny solid particles, which tends to follow the comet's orbital path.
We see that sort of thing with Halley's Comet, probably the most famous one.
Halley's Comet is the classic example, yes. It's a periodic comet returning to the inner solar system roughly every 76 years.
Yeah.
Its visits have been recorded for centuries. And as comets orbit and shed material, they leave behind these long trails of dust particles along their path. When Earth happens to pass through one of these debris trails.
Meteor showers.
Precisely. That's what causes annual meteor showers, like the Perseids from Comet Swift-Tuttle, or the Leonids from Comet Tempel-Tuttle. The tiny particles burn up in our atmosphere. Historically, of course, comets weren't seen as just dirty snowballs. Their sudden, spectacular, and unpredictable appearances often led them to be viewed as bad omens, harbingers of disaster or major change. #B, stellar life and death.
All right, let's shift again, now looking at how stars evolve, particularly the more dramatic parts of their life cycle. Let's start with the nebula, often shown as these beautiful glowing clouds of gas and dust. An interstellar mist.
Nebulas are truly fundamental to the cosmic story. They play this incredible dual role in the life and death of stars. On one hand, you have vast, cool, dense clouds like the famous Orion Nebula. These are essentially stellar birthplaces, giant star nurseries. Within these clouds, gravity slowly pulls clumps of gas and dust together. These clumps get denser and hotter, eventually igniting nuclear fusion at their cores, and new stars are born. So creation happens inside nebulas.
Okay, so they're where stars are born. What's the other role?
The other role is related to death. Nebulas can also be formed from the material ejected by dying stars. This brings us to one of the most spectacular events in the universe, the supernova. A supernova is the incredibly powerful explosion of a star, a true cosmic detonation. It happens primarily in two ways. Either a massive star runs out of fuel and its core collapses catastrophically, or a white dwarf star in a binary system pulls too much material from its companion and triggers runaway nuclear fusion.
And these explosions are unbelievably bright.
Unimaginably bright. For a brief period, a single supernova can outshine its entire host galaxy, blazing with the light of billions of stars.
But the importance goes way beyond just the light show, right?
Oh, absolutely. This is one of the most profound connections in the cosmos. Supernovas are cosmic forges. They are the primary source of all the heavy elements in the universe. The fusion inside normal stars can create elements up to iron. But it takes the incredible energy and pressure of a supernova explosion to fuse lighter elements into heavier ones. Things like gold, silver, lead, uranium, essentially everything heavier than iron.
So the stuff planets and we are made of.
Exactly. Supernovas literally seed space with heavy elements. They blast this newly created material out into the interstellar medium. This material then mixes with existing gas and dust clouds. It eventually becomes part of the raw material for new stars, new planets, and potentially new life. The iron in your blood, the calcium in your bones, it was all forged inside ancient stars that exploded billions of years ago.
We are made of stardust. That's not just poetry, it's literal.
It is quite literally true. And the expanding shells of gas and dust thrown off by these explosions, the supernova remnants, they themselves often form beautiful, intricate nebulas like the Crab Nebula. So the cycle continues. Nebulas form stars, stars die in supernovas, supernovas create heavy elements and form new nebulas. It's cosmic recycling on the grandest scale.
Okay, let's bring our view much closer to home now. We need to nail the precise C1 vocabulary for our own appearance, the lunar cycles. Knowing these terms is really essential for descriptive accuracy.
Absolutely critical. Let's start with the most obvious one, the full moon. That's when the entire face of the moon, visible from Earth, is illuminated by the sun, the complete lunar phase. Culturally, it's huge, right? Tied to festivals, calendars, folklore, werewolves. But for astronomers trying to observe faint, distant objects, it's actually the worst time. The sky brightness from the full moon just washes everything else out.
Right. Makes sense. Then there's the half moon. Is that technically correct?
It's the common term. Technically, astronomers call these the first quarter and third quarter phases. You see a lunar semicircle. What's great about the half moon phase, especially along the terminator, that line between light and dark, is the contrast. Sunlight hits the craters and mountains at a low angle, casting long shadows. It makes the surface details really pop, which is fantastic for photographers and visual observers.
Okay. And then the opposite of the full moon is the new moon, sometimes called the dark moon.
Exactly. New moon. This is when the moon is between the Earth and the sun. From our perspective, the sunlit side is facing away from us, so the moon is essentially invisible in the night sky. Lunar invisibility. This is the absolute best time for dark sky viewing, no moonlight interfering. And crucially, solar eclipses can only happen during the new moon phase when the moon passes directly in front of the sun.
Got it. And there's that specific verb phrase we use, to go down, meaning for the sun or moon to set?
Yes, to go down, descend, sink below the horizon. It sounds simple, but it's the precise natural way to phrase it in English. We need to wait for the moon to go down before we can start imaging the nebula. It marks that transition from daytime or moonlit sky to the dark night sky needed for observation.
Okay, sticking close to home, let's clarify the terms for space rocks hitting our atmosphere or surface. Impact events. First up, the meteor, the shooting star.
Right. A meteor is the streak of light you see when a small piece of debris could be dust from a comet or a tiny fragment of an asteroid, called a meteoroid, while it's still in space, enters Earth's atmosphere at high speed. The intense friction with the air heats the particle white hot, causing it to glow brightly as it burns up. That's the shooting star phenomenon.
And we see lots of them during meteor showers, like the Perseids you mentioned.
Exactly. During a shower, Earth is passing through a denser stream of these particles left by a comet or asteroid. Most meteors disintegrate completely high up in the atmosphere. And yes, there's that whole superstition about making a wish when you see one.
Okay, but sometimes they don't burn up completely. That brings us to meteorite.
Yes, and this is the crucial distinction. A meteorite is the actual solid piece of rock or metal, the fallen space rock, that survives its fiery passage through the atmosphere and physically hits the Earth's surface. Finding a meteorite is scientifically incredibly valuable. Why? Because they are actual physical samples of objects from elsewhere in the solar system. Time capsules, essentially.
What can we learn from them?
A huge amount. Their composition tells us about the conditions in the early solar system when planets were forming. Some contain organic molecules, giving clues about the building blocks of life. Others, like iron meteorites, tell us about the cores of differentiated asteroids that were destroyed. We can analyze isotopes to date them, understand their history. They provide tangible extraterrestrial materials for study right here on Earth without needing expensive sample return missions. The scientific value is immense. Remember the Chicxulub impactor evidence? A lot of that came from analyzing layers containing meteorite dust. #D, mapping the sky.
Now, how do humans make sense of that vast star field? We impose patterns, the constellation, a specific named star pattern like Orion the Hunter or the Big Dipper, which is technically an asterism within Ursa Major.
Constellations are probably one of the oldest forms of human pattern recognition projected onto the sky. They have immense historical relevance. It's important to remember, though, that the stars within a constellation usually aren't physically related. They just happen to lie in roughly the same direction from Earth. One star might be relatively close, another vastly farther away. It's a line-of-sight effect.
But they were incredibly useful historically.
Absolutely essential. Before compasses and GPS, constellations were fundamental tools for navigation, especially at sea. Sailors navigated vast oceans by recognizing star patterns and knowing how they moved across the sky through the night and through the seasons. They were also used for timekeeping and agricultural calendars.
Related to constellations, but more specific, is the zodiac. What exactly is that, astronomically speaking?
Okay, so astronomically, the zodiac is a specific belt or celestial zone stretching about 8 degrees north and south of the ecliptic. The ecliptic is the apparent path the sun takes across the sky throughout the year, as seen from Earth. Because the moon and the visible planets orbit the sun in roughly the same plane as Earth, they also appear to move within this zodiacal band. Astronomers historically divided this band into 12 segments, often named after prominent constellations located within them. It's basically a coordinate system for tracking solar system objects.
Right. But that term zodiac obviously has very strong cultural associations too.
It does, and it's important we address that impartially. That astronomical division of the sky, the zodiac, became the foundation for astrology. Astrology is the popular cultural tie-in that assigns symbolic meanings and supposed influences on human affairs based on the positions of the sun, moon, and planets within these zodiacal segments or signs at the time of someone's birth.
So astronomy maps the sky, astrology interprets it symbolically.
Precisely. As hosts discussing this, we report on both the astronomical reality of the zodiac as a celestial pathway, and its significant role in cultural beliefs like astrology and checking compatibility horoscopes, without endorsing the validity of those beliefs themselves. We just present the connection factually.
Okay, let's pivot now to human efforts to actually go to space. We need to define the environment first. The term aerospace, it seems to cover both air and space.
That's exactly right. Aerospace is a compound term encompassing both Earth's atmosphere and the region beyond it, outer space. It defines the total space environment relevant to flight and spacecraft operation. Thinking of them together is critical for the field of aerospace engineering. Designing vehicles that can operate both within the atmosphere, like during launch and re-entry, and in the vacuum of space, requires tackling incredibly complex challenges: aerodynamics, propulsion, material science, life support.
And innovations are key. You mentioned reusable rockets earlier.
Yes. Innovations in aerospace engineering are constant. Things like developing lighter, stronger materials, more efficient engines, autonomous systems, and reusable rockets like those pioneered by companies like SpaceX are a huge leap. They drastically lower the cost of launching payloads, making space access more frequent and potentially more cost-effective for science, commerce, and exploration.
Now, what about the specific discipline looking for life out there? Astrobiology, sometimes called exobiology.
Yes, astrobiology, or exobiology, is a scientific field dedicated to studying the origin, evolution, distribution, and future of life in the universe. It asks the big questions. Are we alone? How did life begin? Could it exist elsewhere? Its mission focus is incredibly exciting. Astrobiologists investigate potential habitats beyond Earth. This includes studying Mars closely, analyzing soil samples from rovers for signs of past or present microbial life. But it also involves looking at ocean worlds in the outer solar system, moons like Jupiter's Europa or Saturn's Enceladus. We have strong evidence they harbor vast oceans of liquid water beneath their icy shells. Figuring out how to probe those oceans for life is a major goal for agencies like NASA.
Fascinating. But before we can explore Europa, we have to deal with getting off Earth, which means dealing with atmospheric conditions. Related to Earth's atmosphere, the air around us.
The atmosphere is the first hurdle, literally. It affects space travel in multiple ways. Launching through it requires overcoming air resistance or drag. Then there's atmospheric re-entry. When a spacecraft comes back from orbit, it hits the atmosphere at incredibly high speeds. The friction generates immense heat, thousands of degrees. Designing heat shields that can withstand this, often using ablative materials that burn away controllably, is a critical engineering challenge.
And the atmosphere affects things already in space, too.
It does. Even in low Earth orbit, there's still a tenuous upper atmosphere that creates drag, causing satellite orbits to decay over time. And down here, atmospheric conditions, weather, clouds, turbulence, even disturbances in the ionosphere can significantly affect the quality and reliability of signals from communication and navigation satellites. So the atmosphere is a constant factor. #B, agencies and execution.
When people think of space exploration, especially historically from the U.S. perspective, one name dominates: NASA, the National Aeronautics and Space Administration.
Yes, NASA. The primary U.S. government agency responsible for the nation's civilian space program and for aeronautics and aerospace research. It's a massive organization with a huge global influence. Its core functions are incredibly broad. They design and launch scientific missions, sending probes to planets like Mars, Jupiter, Saturn, exploring asteroids and comets. They operate major space observatories like the Hubble and James Webb telescopes. They conduct aeronautics research to improve air travel. They collaborate internationally, most notably on the International Space Station. And they develop new technologies for future exploration. NASA's work really sets the pace for much of global space science.
And the specific projects they undertake are called missions, like a space venture or task.
Yes, exactly. A mission in the space context refers to a specific, planned undertaking with defined objectives. It could be a single satellite launch, a long-duration robotic probe journey, or a complex multi-stage human exploration program. We talk about historic missions like the Apollo missions to the moon, which achieved a specific goal. We talk about ongoing robotic missions like the Mars rovers currently surveying the planet. And we talk about future goals like planning missions to land humans on Mars or exploring asteroids. Each mission involves years, sometimes decades, of planning, development, execution, and data analysis. They define the roadmap of space exploration. #C, travel and personnel.
Now, the people who actually go on these missions, we usually say astronaut, but there's another important term, cosmonaut, specifically for Russian space travelers.
That's correct. Cosmonaut is the term used for an astronaut from Russia, or historically the former Soviet Union. It literally means sailor of the cosmos, coming from the Greek cosmos. The distinction has historical roots in the space race between the US and the USSR. Yuri Gagarin, the first human in space in 1961, was a Soviet cosmonaut, a pivotal moment. Today, the term still distinguishes Russian spacefarers. You'll see both astronauts and cosmonauts working side by side on the International Space Station, ISS, undergoing incredibly rigorous training together. It reflects both the history and the current international collaboration in space.
And the vehicle that defined human spaceflight for about 30 years, the Space Shuttle, a reusable spacecraft.
Yes, the Space Shuttle, formerly known as the Space Transportation System, STS. It was designed as a partially reusable orbital ferry. The orbiter vehicle itself, the plane-like part, could return from orbit and land like a glider, ready to be refurbished and flown again. The program ran from 1981 to 2011. It was a remarkable piece of engineering, capable of carrying large crews and heavy payloads into low Earth orbit. It played a vital role in deploying numerous satellites, conducting science experiments, servicing the Hubble Space Telescope, and, critically, assembling the International Space Station. Its retirement marked the end of an era in human spaceflight.
And every mission, whether shuttle or rocket, begins with that dramatic moment. To lift off, to launch, ascend vertically.
To lift off. It's the moment of ignition and ascent, overcoming Earth's gravity. It's visually spectacular, but it represents an immense engineering feat. Generating enough thrust to escape Earth's gravity well is governed by fundamental physics, like the Tsiolkovsky rocket equation. which relates velocity change to exhaust velocity and mass ratio. Launches require incredibly precise timing calculated down to the second to reach the correct orbit or trajectory. Weather conditions also play a critical role. The entire process underscores the absolute necessity for technical precision and power in space exploration.
Okay, let's touch on some fundamental physics governing how things move in space. Starting with the axis, that imaginary line something spins around.
Exactly. An axis is the imaginary rotation line passing through the center of an object around which it spins or revolves. For planets and stars, it's fundamental to their behavior. Earth's axis is tilted relative to its orbital plane around the Sun. And that axis tilt, currently about 23.5 degrees, is the primary reason we have seasons.
How does the tilt cause seasons?
Because as Earth orbits the Sun, the tilt means different parts of the planet receive more direct sunlight at different times of the year. When the northern hemisphere is tilted towards the Sun, it gets more direct rays and experiences summer, while the southern hemisphere, tilted away, gets less direct rays and experiences winter, and vice versa. No tilt, no significant seasons.
Simple but profound. And the spinning motion itself is called rotation.
Yes, rotation is the act of spinning or turning around an axis or center point. Earth's rotation on its axis is what gives us our cycle of day and night. One full rotation takes about 24 hours. But rotation applies on much grander scales, too. Stars rotate, some very rapidly, and entire galaxies rotate. Galactic rotation is the collective movement of billions of stars orbiting the galaxy's center of mass. Studying the speed of galactic rotation, how fast stars orbit at different distances from the center, actually provided some of the first strong evidence for the existence of dark matter. Stars in the outer parts of galaxies were observed to be moving much faster that could be explained by the gravity of the visible stars and gas alone. Something unseen had to be providing extra gravitational pull. #B, the space experience.
Now, for the experience of being in space, astronauts appear weightless. Is that the same as zero gravity?
It feels like zero gravity, but weightless is a more accurate description of the sensation. Weightless means having little or no apparent weight. Astronauts orbiting Earth on the ISS are not actually in zero gravity. Earth's gravity is still quite strong at that altitude, about 90% of what it is on the surface.
So why do they float?
Because they, and the station itself, are in a constant state of free fall. They are continuously falling around the Earth due to gravity, but they also have enough horizontal velocity that they keep missing it. This state of perpetual free fall cancels out the sensation of weight. It's technically called microgravity.
Okay, free fall. And they have to train for that unusual feeling.
Oh, definitely. Being weightless affects everything: movement, coordination, even bodily functions. Astronauts undergo extensive training to adapt. One key training method involves parabolic flights. Specially modified aircraft fly in the series of steep climbs followed by sharp dives. During the dive portion, the plane and everyone inside are essentially in free fall for about 20-30 seconds, simulating weightless conditions. It allows astronauts and scientists conducting experiments to experience and practice in brief bursts of microgravity. #C, the boundary of knowledge.
All right, our final term pushes right up against the edge of what we know and delves into popular mystery. Unidentified flying object, or UFO.
Yes, UFO, or more recently, the official terminology has shifted towards UAP, unidentified aerial phenomena. The definition remains similar. A mysterious object observed in the sky, an anomalous aerial phenomenon whose identity cannot be readily explained by the observer. Historically, terms like flying saucer were common, and often, particularly in popular culture, these objects are assumed by some to be potentially extraterrestrial spacecraft.
But there's been more official interest lately, hasn't there?
There has. It's important to separate the cultural phenomena from the actual reports. The reality is that reliable witnesses, including trained military pilots and radar operators, do report observing objects or phenomena that they cannot immediately identify. In recent years, governments, notably the U.S. government, have shown increased willingness to acknowledge these reports and establish formal processes for collecting and analyzing UAP data through official inquiries. The goal is to try and understand what these reported incidents represent, whether they pose a security risk or if they can be explained by known technology or natural phenomena.
So, investigation is happening. What's the general scientific perspective?
From a scientific standpoint, the approach remains grounded in evidence and testable hypotheses. While the official inquiries focus on identification and potential threats, the broader scientific goal when encountering unexplained observations is usually to seek rational, natural explanations. Often the effort is to systematically debunk UFOs or UAPs by finding prosaic causes, misidentified aircraft, conventional or advanced drones, atmospheric phenomena, ice crystals, weather balloons, optical illusions, sensor errors, or even celestial objects like planets or bright stars seen under unusual conditions. The standard scientific bar for extraordinary claims like extraterrestrial visitation requires extraordinary evidence, which hasn't yet been presented publicly in a verifiable way. So it remains a compelling area where official investigation meets scientific skepticism and ongoing analysis.
Wow. What an incredible journey through the vocabulary of the cosmos. We've gone from the vastness of the Big Bang and the structure of the cosmos right down to the specifics of lunar cycles and the difference between a meteor and a meteorite.
We really have covered a lot of ground, haven't we? We've aimed to equip you, the listener, with precise C1 level language, so you can talk confidently about complex topics, whether it's aerospace engineering challenges, the search for life in astrobiology, the significance of dwarf stars, or the cosmic recycling power of a supernova, that cosmic detonation. This deep dive really shows how terminology isn't just about labels. Sophisticated language genuinely shapes how we perceive and articulate the universe. Knowing the right word allows for clearer thinking and communication about these complex ideas.
For me, the big takeaway was really grasping the implications behind terms I thought I knew. Like understanding why the new moon is crucial for astronomers, not just that it's dark, or how galactic rotation points towards dark matter. That's the kind of C1 precision we were aiming for, I think.
Absolutely. That's moving beyond definition to true understanding and application. Okay, so here's a final provocative thought for you to ponder. We talked quite a bit about how gravity, through things like galactic rotation, structures galaxies, holding stars in orbit. Now, if we take that idea of the cosmos as a systematic whole, an ordered entity, what fundamental law or principle, perhaps one we haven't even conceived of yet, might govern the structure and evolution of the entire universe on its largest scales? Just as gravity governs rotation locally, is there an unseen axis or organizing principle for the whole cosmos? Something to think about next time you look up at the stars.
A truly cosmic question to end on. Brilliant. If this starry guide inspired you, if it helped launch your English language skills into a new orbit, please do support us. Like this video, share it with fellow learners, and subscribe to this YouTube channel to continue joining us on these deep dives. We'll see you on the next mission.